let's look at this problem. This is actually from my dynamics video 32. All right, so in this problem, we have this 18 kilogram wheel. It is rolling while slipping, so we already know that it is slipping. And there's a force applied to through this handle to its gravitational center. This force is 300 Newton with a 10-degree angle with the horizon. And the radius of gyration kg is given. That saves some trouble to calculate the mass moment of inertia about an axis passing through its gravitational center g perpendicular to the screen. And we need to determine the angular acceleration of the wheel as well as the linear acceleration of its mass center or gravitational center. We're given the coefficient of kinetic friction between the wheel and the ground. So this is for this problem, we actually do not need to make any kind of judgment when it involves friction, because we already know that the wheel is slipping. We are going to again start with free body diagram. So for this wheel, we have the weight force. The weight force equals to 18 times 9.81. And then this 300 Newton force is applied here at point G, and we can resolve it using trigonometry into horizontal component and vertical component. So its horizontal component equals to 300 times cosine 10 degree, and that is 295 Newton. And its vertical component is 300 times sine 10 degree, and that is 52.1 Newton. And of course, we have the normal force from the ground. And we already know that the wheel is rolling and slipping, and the force is pushing the wheel to move in this direction. We have a force directly acting on this at this center, pushing it to move to the left. As a result, the impending motion is to the left. This is the direction of the impending motion. Therefore, friction acts to resist impending motion. Therefore, we have kinetic friction here, which can be easily evaluated as mu kn. So that is the free body diagram. And we need to also draw the kinetic diagram. For the kinetic diagram, this is a point G. Point G only moves to the left with the acceleration. Let's just call it ma, because there's no other linear acceleration. We already know that the center of this wheel will only move to the left. And because it's rolling, we will also have Ig alpha. Ig is the mass moment of inertia about point G, and alpha is its angular acceleration. So now we're ready to write our equations of motion. We're going to start with the resultant force along the y direction, because we want to solve for the normal force first. So resultant force along the y direction, up is positive, and that equals to normal force minus weight force, which is 18 times 9.81, minus 52.1, and that equals to 0. From there, we can solve for the normal force, which is 229 Newton. And don't forget, we know for sure the friction is kinetic friction. Therefore, we can solve for the frictional force as well. And that equals to 0.3 times the normal force. And that is 68.7 Newton. And then summarize the force along the x direction. Because the way that I draw my kinetic diagram, so we're going to say left is positive x. So along the positive x direction, we have this 295 Newton force from the applied force minus the frictional force. We actually already know what it is. Let's write it here first, and then 295 minus 68.7 that we solved from the previous step, and that equals to ma, which is 18 times a. From here, we can solve for our acceleration. It's 12.6 meter per second squared. That's the linear acceleration we were asked to solve for. And lastly, we summarize the moment. You can summarize the moment about point G, or you can summarize the moment here. Let's just summarize the moment about point G. Counterclockwise is positive. And the weight force, this applied force, and the normal force do not have moment about point G because they have lines of action passing through point G. So the only force that does have moment about point G is the frictional force with a moment arm of the radius. It's counterclockwise. So this equals to 68.7 times the radius of 0.5 meter. On the right hand side, that equals to Ig alpha. Ig can be determined from the radius of gyration, so m kg squared alpha, which equals to 18 times 0.3 squared times alpha. So in this equation, we only have one unknown, which is alpha. Therefore, alpha can be solved from this equation to be 21.2 radian per second squared. So this is the linear acceleration of the mass center, and this is the angular acceleration of the wheel. And that's the end of this problem.